In this video, we're going to start to look at how to solve filtering problems. And we're going to focus to start with on the linear Gaussian state space model, where this algorithm is called the Kalman filter. We're going to start there because it's easy to sort of visualize distributions. And I'm going to produce a little sort of cartoon description of what the Kalman filtering algorithm involves. The corresponding algorithm for the discrete hidden state HMM is called the forwards algorithm, and it will have exactly the same structure, but it will be using discrete variables rather than continuous variables. So here I'm going to present the sort of the basic recipe for the Kalman filter with, as I said, a cartoon picture to keep around with you. In the next chunk, we're going to dive into the mathematics and prove that the cartoon description here is in fact mathematically correct. But I think most of the intuitions can be garnered from this particular section of the presentation. Okay, so let's dive in. Remember, the computational goal here is to compute the probability of xt, the distribution over the latent variables, given all of the observations up to and including the current time point. And ideally, we'd like to do this in this online way, where as we evolve from one time step to the other, we have a filtering estimate from the previous time step, and we have a new data point yt that comes in, and then we'd like to take that old filtering distribution and that new data point, combine them together to get the new filtering distribution at the current time step. So this is going to be an algorithm which is recursive. It takes in the old filtering distribution at each time point and the new measurement and updates, providing us with the new filtering distribution. And the solution for linear Gaussian state space models was developed in the 50s and 60s. It was pushed forward by a chap named Kalman, and it still bears his name. Okay, so let's start with the previous filtering distribution at the previous time step and show how we can, through a bunch of steps, combine that with the new measurement yt to form the new filtering distribution. And here is my little cartoon picture of this. I'm going to imagine we're in a case where the dimensionality of our hidden state here, x, at any time point is equal to 1. So I can plot these as one-dimensional Gaussians with a particular mean here at the current time step and a particular variance here. Okay, so we're just going to sort of show these schematically and how they change through the steps of the algorithm. Okay, so we start with a Gaussian from the previous time step. That's always going to be shown in black. And then we want to carry out the following two steps. So in the first step, we can do this first step before we've seen any data. And the first step is essentially to make a little prediction about what we expect the value of xt to be, given all of the data up to and including time step t-1. Okay, so we're going to make a little forecast forward in time for what we expect the value of xt to be. This will actually form the prior over xt that will combine with the likelihood coming from the next observation in order to get the posterior. So that will be our subsequent step, and therefore why it's useful. So how do we actually compute this? How do we compute the prediction for what's happening at the next time step? Well, fairly intuitively, what you do is you take your old filtering distribution, which is a distribution over xt-1, and you push it through the noisy dynamics here. So you push it through the recipe for generating xt, given xt-1. And in the linear Gaussian state space case, this means pushing it through the distribution. Let's write this up. This is a Gaussian distribution in xt with a mean in the one-dimensional case, which is given by, let's say, lambda times x of t-1 and some Gaussian noise. Okay, in the one-dimensional case, this is just a one-dimensional Gaussian autoregressive model. And I think in the notes previously, lambda was called A. This is our matrix A, which has become a scalar. and the noise here was called Q. Okay, that's just connecting to our notation previously. Good. Okay, so in this case, in this one-dimensional case, in order to build some picture of what we're doing, we'll take this Gaussian here and pass it through this noisy dynamics. And what that will tend to do is it will tend to smear out the Gaussian, make it a little bit wider because we're adding in this extra noise here. You can view this as convolving the Gaussian with another Gaussian of width sigma. That will smear it out. And it will also typically diffuse the mean back towards zero a little bit, because you remember in many applications, if you want the system to be stationary, then lambda will take a value which is between 1 and 0. Typically, it doesn't have to be the case, but typically that is the case if you're using it in a stationary way. So if you want to keep a little cartoon mental picture in your head about what this step will end up looking like, is it will end up doing something like this. Our prediction for the next time step will be a little bit closer to 0 here, and this thing has moved closer to 0, and it will be a little bit wider. And that makes sense from an inference perspective as well, because we would expect to be more uncertain about the next state in the sequence, the next hidden state in the sequence, than we were about the current one, for which we actually have a measurement yt minus 1 associated with it. So it makes sense that, in fact, the further we would forecast into the future, the broader this Gaussian would get, and the closer to having mean 0 it would have. Okay, great. So this is the first subpart of the Kalman filtering recursion. You make a forecast for what the next state value would be, and that will give you another Gaussian, which is a bit fatter and a bit closer to 0 in general. Good. Now what you do is you take the likelihood arising from the next data point, the probability of yt given xt, you multiply it by the prior, which is what you thought the value of xt would be, renormalize, and that gives you your new filtering distribution, P of xt given y1 to t. And this is essentially just applying Bayes' rule with that forecast entering as the prior and the likelihood term being the normal sort of usual likelihood over x. So what does this look like schematically? Well, imagine we're in a fairly low observation noise case. Our likelihood function might look like this. So remember, this is something specified by our model, the probability of yt given xt. This thing is also a Gaussian distribution in yt with a mean which is given by here. This used to be a matrix, but we're in this case we're assuming x and actually y is scalar, in which case the matrix becomes a scalar C, which multiplies x of t, and then there's some noise which we called r in here. If we imagine this is rather small, the likelihood will be kind of narrow here. So yt gives us lots of information about x of t. And now we just need to multiply this likelihood by the prior here and renormalize. And when we do that, we'll get something that looks a bit like this. It will have a mean which lies between the two Gaussians from which it was made. And because both of these are giving information about x of t, it'll actually be a little bit sharper than both of these Gaussians. And you can see it's sharper because its peak is higher. If things are narrower, they have to be higher to maintain their integral being 1. And this is our new filtering distribution. It's just another Gaussian. And now armed with that, we can take this and push it back into the same recursion. We forecast for the next state, xt plus 1. We multiply that then by the new likelihood function. We renormalize and we carry on all the way through. And you can see naturally this would be an online algorithm for sequentially updating the filtering estimate for x of t. Okay, so this seems fairly intuitive. The next sort of video chunk is kind of an optional one where we're really going to dig deep into the math and show that this is indeed not an ad hoc procedure, but sort of justified formally as the correct way to compute the filtering distribution.